Which of the following compounds will decarboxylate, which means lose carbon dioxide when heated? So we need to know the structural features of a molecule that will cause it to decarboxylate when it's heated. And so what we know about this is that this will happen if you have a carbonyl at the 3 position of a carboxylic acid. Right, so a carbonyl is just generic C double bond O. So that could be any carbonyl containing functional group. It could be an aldehyde, a ketone, an ester, another carboxylic acid, that sort of thing. So we only have 2 molecules here that are actually carboxylic acids. So that would be B and C. And so if we count 1, 2, 3, 4, this one is too far away. But if you look at C, 1, 2, 3, this is what we mean when we say we have a carbonyl at the 3 position. So really quickly, that is the correct answer, but I'm going to go ahead and draw the mechanism for this decarboxylation. So I am going to draw this ester. So I just kind of flipped it around. It doesn't matter. You could have drawn it the other way. But what I am going to flip around is I'm going to spin this bond so I have the OH pointing up and the carbonyl coming out this way. And that's because I want to arrange it so I can have my electrons kind of flow around this 6-membered ring. So this is how this reaction occurs. So having these electrons flow around a 6-membered ring means you have a 6-membered ring transition state. And we know that 5 and 6-membered rings are relatively stable in organic chemistry. So what's going to happen is we're going to show this pi bond from the carbonyl, whatever carbonyl is at the 3 position. It's going to deprotonate here. So it's deprotonating your carboxylic acid. The electrons from the oxygen-hydrogen bond are coming in here to form a double bond. So right here is where we're forming that CO2 from this carbon and these 2 oxygens. So this would be a double bond and a double bond. And then we're going to break this bond. So let's take a look at what this has formed. So we now have an enol on this side of your ester and CO2. And so your CO2, we can highlight this maybe in a different color. I'm not sure if this will show up too well. We'll try. Is these carbon atoms here and that extra lone pair of electrons. So that's where that CO2 is coming from. And then what's going to happen here, whenever you have an enol, it's going to tautomerize back to its carbonyl form. Right? So you can just kind of imagine moving this bond up and a hydrogen down here, even though that's not mechanistically how it occurs. That is the net result. So you'd end up with that.